Hello friends, welcome back. In the concluding week, in this week we will explore some of the case studies for 4D application of the exotic structures. Till now we learned about the basics of 3D, basics of 4D, and then we applied this 3D 4D concept using polymer, metal and gel based printing. We have seen the idea of sensor fabrication, and then we have also explored some of the applications in the biomedical domain for veterinary, for dentistry, for orthopedic application. This particular week is focused on understanding how I am getting the 4D behavior with the use of the exotic structure. Basically, the interest is in the metamaterials. So here we move. So for the understanding of the exotic structure, basically I am interested in negative Poisson ratio. That means I am expanding perpendicular to the compression and contracting under tension. As you can see in this picture, the horizontal traction of re-entrant honeycomb network. So this is a typical honeycomb network. So if I apply a uniaxial strain like 10% to the right, I am getting the Poisson ratio of minus zero point 0.8. That means I am getting the expansion, right, rather than the compression. So, by definition, based upon the fundamental, the exotic material exhibit a negative Poisson ratio, and they expand laterally when stretched and contract laterally when compressed. So, for understanding of the Poisson ratio, this is the lateral strain to the longitudinal strain. So, we are basically interested in using this behavior for developing some 4D material which can be stimulated using let us say the physical load or any other stimulus for a controllable behavior. So exotic material normally they have two specific properties: larger when stretched and smaller when compressed. A lot of people use the kirigami origami structures for the understanding of these type of exotic material. Our civil engineering friends, our friends in electronics domain who are actually working in the area of sensors specifically based on microstrip patch antenna, they use lot of meta structure based exotic materials for generating or controlling the response to their antenna. Then these exotic materials are normal materials, smaller when stretched and larger when compressed. Advantage are like you can have a increased shear stiffness. I can think of increased plane strain, fracture toughness, increased indentation resistance. These are superior to conventional materials in many practical applications. Like one typical application, I normally give an example. Like take the example of a railway bridge. So in a railway bridge, we are exposed to the concept of trusses. So the final modulus of toughness that I am getting for that structure is not dependent upon the inherent property of the material, but the length of the link and the angle of link that is more important to give me the same modulus of toughness. So I can think of a reduced sectional weight along with the superior mechanical properties. So in typical 4D applications, now we will see how we can implement this first for the metal printing case. So exotic structures, as we know, are remarkable for their unique mechanical properties, specifically because of the negative Poisson ratio. So this presentation I have prepared in a way that the fabrication of such type of exotic structure through 3D printing is little clear to us, right? So before actually I make these type of structures using a 3D printing, let us understand some more detail about the exotic structure. So these are material with negative Poisson ratio, like conventional materials. Once I am stretching it, it is not getting thinner, rather it is getting thick, right? So it has a unique mechanical property. I can think of tuning of the mechanical properties. I can think of stiffness. I can think of enhancement in resistance. I can think of improved energy absorption capabilities. The typical requirement can be in the implantation or some type of stunts where I need to have some tunable mechanical properties. Advantage again, like enhanced impact resistance, improved stiffness, versatile design options. So I can think of these type of customized requirement for my veterinary dentistry or the orthopedic requirement. So what is negative Poisson ratio? So here this is the property that is exhibited by the exotic material, where the material expand laterally when stretched and contract laterally when compressed. So this is not traditionally seen in our conventional way of manufacturing, but specifically if I am using the different type of links with the length of the link and the angle of the link, that is responsible for a controllable Poisson ratio. So negative Poisson ratio has some implications also. The negative Poisson ratio leads to enhanced stiffness, energy absorption, impact resistance, making exacting structure particularly suitable for various application in biomedicine and aerospace. Like one of the typical use can be like in case of implants, if I'm using a solid implant, right? So there is a typical problem of stress shielding. So with a negative Poisson ratio, I can basically address that stress shielding problem, right? So in 4D printing, it can be a fiber reinforced exotic structure, like with the enhancement or the reinforcement of the fiber material. I can think of using the exotic property. I can think of using the shape memory polymer, and this can be finally used for the 4D printing technology, right? It is basically having a adaptive behavior. It is reconfigurable, uh, help in shape transformation, lot of application in soft robotics and the self healing properties. Like to add the flavor to this, we have a typical concept of phagocytosis when we talk about the wound healing, right? So if I use, let us say, some bandage which is basically enhancing the process of phagocytosis, in which phagocytes are formed at the different locations and the wound healing take place. If I have a a bandage like this which help me in self healing, and it is made by using the different exotic structure, this can be a great help and can finally promote the wound healing in an exponential way. As regard to the energy absorption and impact resistance, of course it has a lot of application. These are lightweight structures, and specifically the material saving is there, cost saving is there, and specifically in implantable application, this has a lot of meaning, right? In case of the biomedical application, like I have already explained, we can think of using it in the bone implants, we can use of thinking it in the drug delivery, we can think of using it in the tissue engineering applications. Now coming to the fabrication part, specifically if we are interested in metal based technology, people have reported using the selective laser melting, then electron beam melting, direct ink writing. These type of technologies, of course, all are having a layer by layer deposition concept for making these type of the exact structure. Nowadays, DED is also very common if I am interested in making a 4D printed exotic structure with a functionally graded behavior, right? So there are some challenges and future traction for 4D printing of exotic structure. Like one of the challenges is in the optimization process. Another challenge is in the cost reduction, because a lot of research is required for the fabrication of cost effective material. Then scaling up, taking it to the TRL level 7 and 8 is still a thing of the future, because at TRL 4 5 people have developed in the lab, but in actual production stage this is a challenge. Now, let us see one example in the form of case study, where we are interested to develop a typical exotic structure in 3D printing application involving different metallic alloys. Like I have taken a case like in previous reported studies, people have used titanium based alloys, nickel based alloys, stainless steel based alloys, and their powder for making a functional prototype using laser powder bed fusion. In this case, we are using a direct metal laser sintering for the fabrication of the component. So all these metallic powders are quite common, and number of studies have been reported on making the functional part using these type of metallic powder. But if we are interested in, let us say, the functionally graded material, in which two different powders, like up to certain depth, there is a material X, then there is a material Y. Like in this case, this study is reported for stainless steel and nickel 625, that is basically a inconel. Both are biocompatible material, and we are interested to make a functionally graded implant. So for the sake of comparison, two type of metastructure, one is phelon and another is dodecahedron. This has been explored and compare in the form of metastructure. The ultimate aim is to have a tunable properties. Basically, at the end, we are interested in reducing the stress shielding effect, and of course, we are interested in their in vitro analysis, so that the corrosion rate can be controlled. So, in this study, the dodecahedron as a metastructure or as a exotic structure resulted into the tunable corrosion rate with a less Young modulus as compared to Finland, which has shown a corrosion rate of 0.023 mm square per year with a relatively higher Young modulus. Now, in most of the mechanical studies, we are normally interested in improving the mechanical properties. But here in this case, our aim is not to have a higher mechanical property, but to have a mechanical property near to the natural bone. So this is a reverse case where I am interested in tuning my, let us say, the Young modulus near to the human bone, so that there is a better compatibility. So as you can see over here, these are the typical structures that are available. Like this is a as you can see in figure A, this is a dodecahedron structure. So different nodes, their link, their length, angle, etc., these has been fixed. Similarly, this is in this picture B, you can see this is for the dodecahedron, and this is the printed part. So this is 174 pH stainless steel here, and lower part, and the this is the bottom or the lower part, and this is the upper one, and in between I have used a metastructure of nickel 625, which is basically inconal. And you can see over here, this is the case with the uh, dodecahedron, and this is the case with the fill and infill structure, and their number of nodes, etc., we can basically control, right? And these are the tensile specimens that have been prepared. Now, what will happen? You can see the length of the link and the angle of the link is different, right? In both the cases, if I just compare the two, this is just for an sake of an example. I am interested to have a tunable, tensile property. Similarly, we can think of tunable compressive property, tunable torsional property. So this help me in a big way of controlling, the implant properties, just customized or tunable near to the natural bone. So that is one of the advantage or the flexibility that I am getting with the use of this type of the metal printing. So this is the actual printed part. You can see over here dodecahedron, and here is the fill-in structure. This is the setup that we used, and these are the corrosion testing. Basically, the we have used the potentiostat for the measurement of the corrosion rate, and we try to follow the ASTM codes and calculated using a potentiostat the open circuit potential, polarization resistance, and finally we try to develop the Tuffle plot. Right, so the standard formula for, we have already seen this for the corrosion current and the corrosion rate, and beta node and beta cathode were calculated. So this is the typical Tuffle plot that has been prepared for the dodecahedron, and this is for the phelon. Now this is the comparison. You can see over here, when I am using a dodecahedron as a metastructure, I am getting a exposed area like 50.98 in mm square. When I am using the phelon, I am getting a higher exposure area, and when it is a solid one, the exposure area was something like 40. So what is the polarization resistance, corrosion rate, corrosion current, beta node, beta code, the all things are available to me now. The advantage that I am getting out of this is I can basically tune the properties of my structure in a way that if I am interested in higher corrosion or a lower corrosion rate, I can basically control the exposure area. If I am interested in controllable mechanical property, I can also control that. If I am interested in having a suitable Young modulus, accordingly I can think of applying a particular auxetic structure in a particular zone and the another auxetic structure or the combination in a different zone. So I can basically tune the final component. That is the job of a interest job for me, so that I can have a tunable properties, 4D properties for my implant. So accordingly, we use the ASTM B276 for the porosity analysis and ASTM E112 for the grain size number analysis, and we try to correlate, how the in vitro behavior of the dodecahedron is related with the porosity part, how it is related with the grain size part, and we can basically have a suitable solution for the basically for addressing the stress shielding problem. And of course we can do some further study as regard to use of some bone material density using the x-ray basis analysis, and of course for the implantation purpose some clinical trial can also be taken. So this is the one typical case study that I want to discuss with you. In my next discussion, I will show you some more case studies on metal 3D printing part, and that will be further elaborating on using these type of the exotic structure for tunable behavior. I believe the information is helpful to us, and of course, this can be applied in a any metal printer, as this is a open source technology, and I can think of using n number of materials with n number of infill, n number of static structure. Only the thing that I have to understand is what is my end user application. In some cases I am interested in maximizing the property, in some cases I am interested in minimizing the property. Accordingly, I can tune my links, I can tune my length of the link and the angle of the link. I believe the information is helpful to us, so keep watching. In my coming presentation, I will be explaining first few case studies on metal, followed by the polymer and the gel printing for the use in the exotic structure. Thank you very much. Keep watching.